So now that we understand creativity, we need to apply that creativity. And the best vehicle for doing that are problems. And so that brings us up to the next part of our innovator's mindset, problem solving. We're going to talk about the nature of problems, the mechanics, what are the pieces that you look at, and how do you go about solving. So what drives problems? It's what kind of category they are, what kind of scale are they, and what kind of uncertainty does it create? What kind of risk? Those are the things that drive problems. There are really only 5 different kinds of problems that you deal with. One is numeric, very definitive in how you go about solving it. Scientific, that there are certain laws that you have to look at. Business problems are somewhere in the middle between more social sciencey and numeric. Then we have social science issues like global warming, those sort of things. And then situational, which is something that you face yourself. Naturally, the more quantitative the problem, the more definitive your answers are going to be. Here's the nature of a problem. You have a big problem. How do you go about solving it? What you do is that all big problems are just a collection of little problems, and the little problems are solvable. You solve each piece and then you bring it all back together. You learn to partition the independent parts so you know what little problems you have to solve, and this is what engineers learn how to do. In terms of the spectrum in uncertainty and knowledge, a task means you have something where the information is known, and then you have high uncertainty, and that's that you don't know where to go, what direction to go in, or the size of the challenge. Derivative means you don't know the answer, but that you have a foundation of information to work from. However, not all problems have definitive answers, and uncertainty naturally raises a chance of failure because nobody knows the answer. And this is what we refer to as risk. What is risk? It's the probability something will happen times the severity of the outcome. We normally associate a risk with something negative. Pieces of a problem is first, there's the objective. What is it? Where you're trying to get to from where you are right now. There's an overriding rule which dictates where the solution is going to be. And this is what I keep talking about, the nature of things. The landscape is the information that you get from understanding what's going on around the problem. And so these are the boundaries. The situation might be biased. The time sequence. How much time does it take you to go through it? And how many cycles do you need to go through of learning? And finally, what are the inputs? Essentially, what are the rules? What are the resources that you need? What do you have to put into it? So you start with an objective. And based on that objective, there's a governing rule that dictates what's effective. You have a whole bunch of variables which define that governing rule. And then you have conditions which are dependent. The thing is, between these variables, they might overlap. You have cross dependencies. And typically, these are contradictory. But that's your opportunity. If you can solve that contradiction, you have invention, you have innovation. That's where your opportunities sit. When you assess a problem, you start out being unbiased. Forget about the past. What is my objective? Is it SMART? Meaning if it's specific or measurable, attainable, relevant, and timely. It's got to be tangible. It just can't be like, do your best. I mean, what does that mean? What is the distance when you have to solve a problem? How far do I have to travel to get there? What variables do I have to deal with? And how do I make it manageable? Meaning you're better off with 12 one-month goals than one 12-month goal. You have to make it manageable so you can measure your progress and see that you do have progress. You have to, when people have problems, they go in and just start attacking it. It's better off if you let the problem come to you. Take a step back and understand its nature. Learn to see the foundation of a problem. All things follow some set of rules. Here's the thing about engineering, for example. The thing about engineers is they require large chunks of time to do something. So why on earth do people schedule meetings in the middle of the day? It doesn't help your engineering. Basketball. What is the entire point? What is the nature of basketball? Well, it's to win, right? And how do you win? You score more points than somebody else. And so how do you get points? It's how many possessions you have times your shooting percentage. So you can have a lot of possessions and not have to shoot very well. That's one way of getting a lot of points. Or you could be a great shooting team and therefore you don't need as many possessions. And then you can get into details. Okay, what defines a possession? And so all of a sudden things like steals and rebounds and everything else start playing into it. That's the nature of basketball. Here's a problem that you can solve. And that's that you are on the passenger on the HMS Titanic. You just hit an iceberg. What do you do? Well, the first thing is a lot of people on the Titanic didn't even know they were sinking. And the captain and all the crew was telling you, well, the boat's not sinking. I don't know. We hit that thing pretty hard. And so instead of, again, challenge assumptions, what I'd probably do is like find a can or a ball somewhere, put it on the deck and see whether or not it starts moving. Give it 15 minutes and naturally it does start moving. So, geez, we're going down. So what do you do? Now, most people just put on their life jackets and started running for the lifeboats, thinking that was going to save them. What they didn't know is the Titanic didn't have enough lifeboats. So looking at the situation, seeing how many people there are, how are you going to survive? So we want to survive Titanic. So the objective is we don't want to die. That's the problem here. So what are the most likely ways that you can die? Well, one is I can drown. And how can I drown? Well, one is I could try to swim for it, and I may not make it. However, what's the likelihood of drowning by swimming? The sea's calm, you have life jackets, so the odds really aren't all that great. Now, another way I can drown is when the boat goes under. There could be a vortex that pulls me down. So how do I avoid the vortex? Make sure you get away from the ship and don't get caught in it. What's the other ways I can die? Well, freezing to death. So how can I freeze to death? Well, a lot depends on what kind of media is my body in. And so if I'm in the air, I could just freeze to death standing on the deck of the ship. However, if I wear a winter coat, I could probably last there for several hours. Now, what if I end up in the water? How do you avoid freezing to death? Well, the reason why you freeze to death is because the heat in your body is drawn out into the water, and it keeps pulling heat out until finally your body temperature drops and you die. That's one thing. It doesn't take a big difference, maybe only 6-8 degrees, to pretty much kill you. And so what I'm trying to do is to keep my heat inside my body. And at that point, you have to look at what technology exists. And one way to do it is think about how the English Channel swimmers actually kept the heat in their body. And what they did is first they greased themselves down. And then after that, you can layer yourself with all kinds of what you can basically do is make a wetsuit. So you wear coats and stuff like that and then put on rain gear. But water is going to get in. So how do you stop it? Well, there was tar available. So you can seal yourself in tar and you can have a wetsuit. Not only that, but since you know, if I go into the water, I'm likely going to freeze to death. So I need to stay out of the water, which means let's build a raft. And there's all kinds of stuff on that boat that could float. For that matter, you could probably have taken a bathtub and plugged the drain and sealed it up with tar or whatever. Your main goal basically is to try to get to a lifeboat, or if nothing else, at least you can hang around next to the lifeboat so you can go along with other survivors. But as you could see, you had 2 hours, and that's one of the big tragedies of Titanic, and they put the faith in the people around them, and unfortunately they were overwhelmed. But this is what I mean by the nature of the problem. The nature of the problem of Titanic is don't freeze to death. This is the way you solve problems. You brainstorm. Remember last time we talked about having discussions? You brainstorm. You have all these ideas, and then you have to organize those ideas. This is what I mean by telling a story. Okay, what is the story of our situation? And so typically what people do in brainstorming is you have someone up at the board and they keep writing down what everybody says, and then you take a step back, look at it, and through conceptual thinking, think about how do these pieces come together. That's the nature of problem set. Solving problems. Excuse me. Too much MIT on my mind. Anyway, we keep coming back to this. Economist thinking. Don't think about the past. Think about where you are. Attention to detail and understanding the layers involved. And that's just what we went through before. The architect steps. This is why these mindsets, you keep coming back to it over and over again of how these techniques are solutions. Problems with defined goals, you could do it through induction or backward induction. Induction means what we did. You walk through it. You move forward through a problem. But you don't know what that conclusion is going to be. If you know what the conclusion is going to be, then you can do backward induction. And that's that you start at the end and work your way backwards. That's the thing. And you could do what I used to do when I used to do proofs in math, is I go forward and get stuck. So I go to the end and work backwards and then see how much of a gap I had and fill those in. And this is actually consideration when you look at games. Here's another example, and I apologize if this offends anybody because I know we have veterans and stuff like that. But I was against the Iraq War, and it wasn't very popular. But why was there a call for war? And through inductive thinking, it had to do with stopping weapons of mass destruction. And of course, the question is, are they really there or not? So let's just assume it's true and move forward with the problem. Here's the thing about this entire Iraq War thing. How many needed to be smuggled out for there to be a national tragedy? 1. Is invasion really a good solution to stop this? Yeah, maybe a 10% chance at best. But basically, you cannot seal off the entire country. In all the chaos and everything else, something's going to get out. And the other thing that they never really talked about is how do you frame the problem? The thing is, we didn't have the money to fight this war. So the other thing they also didn't think about, and this is when nobody thinks about war, when a war ends, you just can't leave. If you don't invest the money for peace, you'll just have another war. And that's how come we had to dump tons and tons of money into Iraq. And what have they done? We made them democratic, and they choose to side with Iran. Yeah, that worked out real well for us. Here's the thing where I got on George W. Bush about. Not that I ever talked to him, but he said, we want democracies. We don't want democracies, we want friends. That's what we want. Nobody gives a damn if another country has freedom. All we care about is, are you going to be a headache to us, or are you going to be one of our friends? Not only that, but to fight this war, we're going to have to incur more debt. And China was likely to pick up that debt. And so, all of a sudden now, when you frame that war, should we have gone into a country where we had no guarantee of stopping a WMD, even if we did, and go into debt for China for it? All of a sudden, I think the American people wouldn't have wanted it. But then again, I'm heavily anti-war for a number of reasons. One thing about wars is they always lead to another war. Is it really worth getting involved with? The other problem because war starts a cycle of violence, and I've seen this firsthand. And that's I hit you, you hit me, I hit you back harder, you hit me back even harder. And it becomes a cycle, and it's a cycle that you can never stop until everybody's dead. So to me, it's just not worth it. Not only that, but the sheer cost I mean, look at the amount of work that goes into an aircraft carrier. I mean, it's insane, the amount of materials and everything else. And I'm sure the aircraft carrier was the inspiration for the Death Star. Because that's what they really are. They're city platforms. You've got like 3,000 to 5,000 people on that aircraft carrier. Anyway, enough of my pontificating. On the other hand, I was in favor of the Afghanistan war. And part of it is because that's where bin Laden was hiding. You didn't have a choice. In that situation, you can't show weakness. Anyway, through inductive reasoning and looking at the challenges of the assumptions, all of a sudden, that Iraq war doesn't look so great. So the first kind of problem we have are numeric. And here's the nature of things of a numeric problem. Math is about conditions. Do you have enough information to go through a process to solve that math? Differential equations, calculus, addition, subtraction, division, they're all processes. And the processes with very well-defined outcomes. To think about a differential equation, it's all about boundary conditions. And if you have enough boundary conditions, you can solve it. And you have definitive. That's why math problems are the easiest to solve. What about engineering in science? This is where Elon Musk gets into his fundamental principles. This is a micro cantilever. It's used in sensors. These are the structures that go into gyroscopes. All of you have accelerometers in your cars. And this is about 5 microns thick. To understand what 5 microns is, a hair is about 100 microns. That's how small this stuff is. In order to do this, though, it needs to be rinsed in water. And what happens is when the water goes out, this sticks to the bottom and can't move. And so the question is how do you avoid that stiction? What stiction is a function of is the molecular adhesion between two materials, meaning some materials will stick together, some won't. How much surface area, how much contact area do I have? And then how much restoring force do I have? Meaning, how much force do I have that's going to pull it apart? And so that's how I solve stiction. Now that I understand what the fundamental principles are, what the fundamental variables are, I look at each and figure out what is it that I want to deal with. And so restoring force isn't a good option because the entire sensing is about how much this thing bends. And so you make it less sensitive, the stiffer you make it. So restoring force isn't. UC Berkeley decided they had the solution to this all. They decided to go after the molecular adhesion. They put a surface coating to prevent it from sticking. And we tried it, and the stuff was greasy. They were still stuck. I mean, I don't know where they got the data from their paper, but it was a disaster. It didn't work at all. And so I looked at the problem and I said, let's go after surface area. And what did I do? Instead of having a flush contact, for those of you who ever put two smooth pieces of glass together, can you pull them apart? No, you can't. It sticks together. That's how come you have to shear it to get it apart. And that's what happens when you have really, really smooth surfaces. They'll just adhere. And the reason why they'll adhere is a smooth surface, you're going to have more atoms. You're going to have more things touching. And those molecular forces will get attracted to each other. And so one way to break a molecular force is to shear it, because the force is vertical. I mean, the bonds are vertical. And so what I did is I just created a bunch of pillars. And the thing is, if the spacing is too far apart, then this becomes a bending membrane, which is what Dr. Cho did in his thesis. So instead of having a bending membrane like this, you just put one in the middle. The thing is, the bending characteristic is to the fourth order of the edge length, and all of a sudden now, by sticking this in the middle, I've cut it in half. So 2 to the fourth is I reduce the force by a factor of 16. And so That's how I solved the problem. I implemented it in a day. When you look at business is always a few fundamental problems. Every business problem you could solve this way. It's about opportunity cost, meaning which is going to give me the best ROI based on the amount of cash I have available. Rationality, do I want to maximize my return? There's certain rules in business like supply and demand. They've stood the test of time, and so you have to take those rules into consideration. And then, what's the behavioral motivation? Because there's still people in this business. And this is why engineering and science are more quantitative, but somewhere in the middle, we have business instead of social science. That pretty much covers all the kinds of problems that you're going to see in business. And each one of these has its own nature. And that's what you need to understand. Some microsystems wanted to go into wireless 3G. For those of you who don't remember Sun, they're the makers of Java. They made great hardware. They integrated all together. They offered everything, which is related to a server-type business. And they were wondering, now that wireless 3G was going to roll out, what opportunity to pursue. And so Dr. Cho did some research into it, and I advised my study group we should tell them to go into services. The thing about all technology is it's very complicated, and people don't want to deal with it. So what do? They hire consultants. They have somebody do it for them. That's why, as long as something's complex, there's always a business open for services. There are now over 10,000 digital marketing firms in the United States. And it's because nobody understands it. Here's your proof why they don't understand it. Have you ever seen a crappy website? Yeah, I make my point. Anyway, for those of you who want to learn more, I actually do have a digital marketing class that goes over all this stuff. It's actually a marketable skill. Anyway, so I told them they should get into the services business because they had all the pieces and everything else. And then Scott McNeely, who at the time was considered to be one of the great entrepreneurs, told me to pound sand. And what ended up happening is IBM and HP actually did go into services, and then for the next 10 years, they had more than 10% growth. Some Microsystems, shortly after that meeting, they went under. They were trading at $26 a share. And I told people, dump your Sun stock now. This company just doesn't get it. And within 8 months, their stock had dropped to $5 a share. They missed the opportunity. But not only did they miss opportunity, Dr. Cho missed opportunity. And I can't tell you how much I was kicking myself. The thing is, for a multi-billion-dollar business, 10% growth is like superstar kind of growth. Because when you're that big a business, it's hard to create that much new business. And that's the thing. When you're small, it's not about percentages. It's about the magnitude. And when you get too big, it's not about percentages. But if you have a $10 billion business, think about it. You have to create, for 10% growth, you have to create $1 billion of new business every year. That's not an easy thing to do. So I was right. That was a good opportunity, but there was a better opportunity. And this is the nature of things. And what I forgot is whoever gets closest to the customer captures the value. I have forgotten that. And so what ended up happening, who were the winners in that age? Apple and Samsung. Wireless devices. And Sun was perfectly positioned to get into that space if they wanted to. But they didn't. I didn't recognize it. And I kicked myself for it. Remember, focusing out, focusing in. Social science. Social science deals with the construct of organizations and how people organize. And so what it comes down to is, and this is why I kind of think ethics classes are a waste of time. Actually, in my international business class, I got up and I just said, this is all ethics is. There's morality, there's ethics, and there's legal. Morality is the general accepted correct conduct for all human beings, that there is no question about it, like caring for children, don't murder people. That's pretty much across the board. Ethics is about within a societal structure. This is what we believe, how you should conduct yourself. And legal are codified rules. This is one thing that really bothers me about our politicians. And they said, legally, I didn't do anything wrong. Well, what about ethically and morally? And that's the thing about our society. Our conduct has pretty much come down to the only thing you're responsible for is to be legal. This is why we have so many laws. Because if you can't trust people to act ethically or morally, then you have to make everything a codified law. And so that's why it gets so big and messy. But legal is the bare minimum standard of how you should act. A big issue about social science revolves around also one of the biggest problems in the social science problems. Can you or should you do something just because you're capable? Like war technology, at what point do we stop? Social science problems are about the scale of it, is about the many or the few. What is your responsibility? For example, climate change, is it real? I'm one of the few people who actually went through the models. I mean, who's not in the field. I didn't believe anybody. I didn't know if it was real or not. And so what I did is I actually started going through the models. And the thing about chemistry is the nature of chemistry. Again, the nature of things. This is a chemistry issue. Chemistry goes both ways. When people think about equilibrium, they think it's calm. No, equilibrium is dynamic. What equilibrium means is that the equation going in one direction, the creation, is balanced by the destruction. That's the way it works. The thing about CO2 is CO2 can be an indication. As things get hotter, CO2 goes up. But it also works in the opposite direction. If you create a lot of CO2, you can create a rise in temperature. And what we're seeing is, and we're talking about hundreds of thousands of years ago, we're seeing the greatest amount of CO2 ever. And so CO2 goes up. And all these other theories like solar effects and stuff like that, I went through that and I said, this is affecting things 0.2 of a degree. That's nothing. And so we see CO2 go up and then we see the heat rise. And that's the thing about the lag that we're seeing taking place. And that's that when the CO2 goes up, the temperature goes up. And I couldn't get around that. The question is, how do we get people to comply? And how do you get somebody to do something? You either have to converse them, incentivize them, or inspire them. William Shatner, who's 91 years old, recently talked about it. He's become a climate activist. And the reason why is when he went up to space and saw the Earth, he literally started crying. And it's because he said, it's so beautiful and we're destroying it. We have to do something. And so he was inspired. The thing is, very few people really get inspired. We've tried incentives and they haven't worked. And this is why they talk about a carbon tax. Until you make it painful for people, they're not going to act. Here's the thing about people. Pain is worth 3 times gain. This is why entrepreneurs are always talking about the pain, the pain, the pain. And this is why we do it, because it's just a lot easier to sell. Situational. In the situation that you're in, can you figure out where the nature of the competition is? And so once again, we go through the same process. Remember that about how far are we to the end? What are the variables involved? Everything like that. Go through that process. I was at a company picnic, and they decided to have a tug of war. And what happens? All the athletic guys formed one team. And I'm like, oh my God, these are the guys who go out at lunchtime and either go to the gym or play soccer. And who are they matched up against? The fat old guys. We're the managers. We spent all our time sitting in front of computers. And I sat there going, oh my God, we're going to get slaughtered. And nobody wanted to be in charge, so they put me in charge. And so I started thinking through the problem. Who wins in a tug of war? What is the nature of the competition? It's the side with the most force wins. And what is force a function of? Strength, weight, but also traction. For example, if one side was pulling on ice and one was pulling on the ground, then the other team would just slide across. And that determines what the force is. Well, we're not going to win on strength, and we're not going to, the weight was even between the two sides. So I thought, if we're going to win, we're going to have to win on traction. And traction is a function of the surface area of your contact, plus how much friction you have. So we're going to win on traction. What did I do? I told everybody, start digging. So they started digging trenches. Now, these guys, in their genius, I saw them putting on their cleats. And so, them putting on their cleats, I started thinking, And they said, you could pick the place where we're going to have the tug of war. What did I do? I walked around the picnic grounds and I said, we're going to have the competition right here. Well, where did I pick in the picnic grounds? It was baked, hard clay. Remember, traction is a function of area? Well, guess what? Their cleats could not dig in to the ground. And so, therefore, they had less surface area than we do. And we now had trenches. So, what did we do? I would yell, lean, and everybody would lean back. And then we would yell, step, and everybody would take one step from one trench to the other. And just like a ratchet wrench, we pulled them across. So the fat old guys won, not because we were better. We were just smarter. Situation. For example, how are classrooms going to protect themselves against school shootings? And I hope this doesn't become too controversial for people, but it is an actual situation. And what are your objectives? No loss of human life and minimize injury. The nature of the things is this is a risky situation. In terms of responding to risk, I can reduce the effect, I can avoid it, I can transfer it, or I can accept it. Those are the solutions to risk. If you're trying to think of solutions, think of those four things and how we can go about doing it. So the approach is, when we can block, don't let the intruder in. Let's avoid any kind of conflict to begin with. We can evade it, which is hide from detection. We can terminate it, which means nullify the attacker. Or we could delay it. Wait for security to come in. This is also accepting the risk that we're going to assume that we're going to get saved in time. Or we can avoid the risk altogether by just avoiding the situation and finding a way to escape, like breaking the windows and jumping out the window. Even from the third floor, if you can at least, lower yourself as far as you can, extend your arms and let go. That's a 20-foot drop. You're probably going to break an ankle, but at least you're not going to die. And so you have to look at any time you're formulating a strategy. The first thing you do is look at the landscape. And so this is what a typical classroom looks like. Here's one of the flaws in all the doors. They open into the hall and they can't lock. One professor suggested that we lock all the doors and students can just use their ID cards to go in and out. To me, that's a good solution. But you can't lock the door because of fire reasons. And that's the thing. If the door opened into the classroom, we could defend ourselves. The desks are 1-inch metal. We're on the third floor. The windows don't open up. We do have utilities. There's sprinklers. No guns or knives are allowed. And we have about 30 chairs in the room. Part of the technique is, this is a big heavy desk. Put it shut. Maybe we can hide over here. And it was kind of interesting what the students came up with, and what we came up with is pull back the carpet. And everybody's got water in water bottles, drown this area in water, and then one person hide behind here, and then we strip some wires, and then we just basically electrocute anybody who comes through the door. Anyway, summarizing what different problems are about. Math is about processes. It's about paying attention to detail. It's about order. And the thing is, nobody does math anymore. We have too many good computers. Engineering is about figuring out the limits of what you can do, that there are laws that you can't get around. And if your variables conflict, which of the primary variables do you want to work with? It's also about hard work cycles and number of cycles. Solutions in engineering is not about math, it's about insight, and that's why they're separated. Business is about matching and forecasting. How do you connect, and what's going to happen once you deal with this? Not only that, but people are a very large part of it. But business can have math and engineering elements to it. Social science is about the nature of people and the limits of human-made systems. How are people motivated? How do those systems change? And situational, it's about games. When you have a situation, again, uncertainty, it's a game. And what are games about? Who are the players? What order do they act in? What's the timing of it? How much time does each side have? How much am I wagering? What are the payoffs? And what information is available to me? That is the foundation of all game theory. And if you think about things that way, you can come up with solutions. You get good at this through practice. Solutions aren't derived in most cases due to lack of discipline, problems all around you. Even just reading the newspaper, looking at an article on the internet, challenge yourself and ask yourself, how am I going to solve this? Joseph Swan, Henry Woodward, Matthew Evans, and Lewis Latimer, what all these men had in common is they lost to Edison. They all had working light bulbs, but they all lost to Edison. And sunk cost is, how do you learn from what they did? And then after that, don't repeat and do the way they did things. What is your objective? That's what everything starts with when you're solving a problem. What is the objective? And the objective was to make a light bulb, and the reason why their light bulbs failed is it wasn't due to brightness or power. It had to do with the fact that they didn't last 1,200 to 1,500 hours. But the other thing is, cost was an issue, how bright it was going to be, the light quality. And some of you have probably been through that you can get headaches. Remember, this is the process that you go through. When you do problems and can't remember, look these steps up again. What is the distance? Well, the distance is that the light bulbs only work for 13 and a half hours, and we're trying to get to 1,500. The cost, it was $1,000 an ounce. They were using platinum, and you want to get to 2 cents. Power, it was burning 70 watts. You want to get down to 20 to 30, and also you want to get more than 8 lumens per watt. What are my variables? What materials I pick? How am I going to package it? And what power can I assess? And what it came down to is the race was on, and it took Edison a year. The fundamental problem of the light bulb is the filament would burn out. And so, what did Edison come up with? How did he solve it? If something is going to burn, it means it's oxidizing. Edison thought, well, if it's going to oxidize, why don't we just get rid of the oxygen? And so what he did is he took his light bulb and he put it inside a vacuum. And all of a sudden, it lasted a very long time. Plus, he came up with a better filament that was actually much cheaper. And so Edison built a greater vacuum pump. He actually looked at the fibers in bamboo and carbon coated them. And so what happened is that Edison closed the distance. It worked. In terms of gas efficiency, in terms of solving that problem, we're concerned about emissions. Is it about the electric car, or is a hybrid more acceptable? I personally like the hybrid electric, and the reason why is gasoline is still going to be around for a few decades. And so, when you get transit, this allows you to have the best of both worlds. Because let's face it, there's one thing you can't get around gasoline. Other than nuclear materials, gasoline has the most power per gram or per liter. You just can't get around that. And that's why we use fossil fuels. The problem is, again, nothing's for free. And so the problem is that how do we transition away from that? And it's not going to happen abruptly. COVID-19, do we use the right approach? And the objective is we don't want to shut things down. We want to allow people to be active. But how many people will we accept as being acceptable for dead? And this is the big problem with COVID and what the problem was at the time. And that's that what people didn't understand is, yes, the death rate is low, but the reason why the death rate was low is because people could get hospital care. So therefore you have like 1 or 2% of the people dying. On the other hand, if you do not control it enough, then you overflow the hospitals, and now you're looking at 10% of the people dying. And that's what happened in Italy. And what a tragedy. So how do we fix COVID? Well, one approach is to come up with a cure. And there's a reason why we don't have a cure for the common cold and a lot of other things, because viruses tend to mutate. And because they tend to mutate, the way we go after viruses is basically we introduce some kind of attacking cell, and the proteins are attracted to each other, and that's why it knows to target it. Here's the problem. If the proteins are constantly changing, then the attacking cells don't know what they're going after. When HIV came out, my little brother, who's a biochemist, he said to me, "These people are crazy. We're not going to come up with a cure anytime soon." And he said, the virus just mutates too quickly. So we're probably not going to come up with a COVID cure. We can block it. And that's what vaccines are about. And today, I'm happy to say that we get about 400 COVID deaths a day. Now, not that 400 is good, but having a death rate of about 15,000, considering right now in the United States, we've had, 1.1 million people have died since COVID started. We're now talking a death rate less than the flu, and the flu is considered to be acceptable. And every flu season, anywhere from 300 to 600,000 people die, and we consider that to be acceptable. So that's the acceptable range for COVID. Or we can contain it, which means test and quarantine. The Ebola pandemic. Let's see, the Zika virus pandemic. Why did you never hear of these? It's because Barack Obama had a very proactive CDC. The moment it happened, they quarantined people off and stopped it from ever spreading. And the thing is, we could have taken measures right away. The problem is that wearing masks and things like that, people just complain too much. And so that was the problem. And this is why countries like South Korea and Taiwan had death rates about 100 times less than we did. And they didn't shut down. They didn't need to shut down because everybody cooperated. Look, your options are we shut down or everybody basically also become traceable. And the Koreans and the Taiwanese decided, yes, we're going to go do this. So they've done quite well. And one last note about problem solving, this perspective, is you can't judge things by hindsight. Anyway, now that we've gone over the core concepts, we now move on to technical approaches, the groove.